Well, solar sounds pretty good, right? It's fairly clean, doesn't produce carbon. Seems like a pretty sweet deal, but it has its problems. The primary problem with solar, and this is mitigated a little bit in the case of heliostat, but it's still a problem for them, is the amount of energy generated as compared to the time that we need that energy, especially if you just look at the course of one day. So I love this figure here. You can see this is shown in gray. This is essentially our kind of natural power curve. We don't use much power in the middle of the night. We wake up, kick on the coffee, turn on the radio, do whatever, use our electric toothbrush, razor, or something like that. Maybe turn on some lights. But then generally we go to work during the week, and so during the day, our individual homes also use a fairly low amount of energy. And then in the evening, you come home and kick on the TV or fire up the Xbox or start cooking dinner with an electric stove, and we have our spike in the evening. So for a city, right, so the amount of power consumed in the Treasure Valley, let's say, in our local area, this would be the curve that we would expect, right? Our morning pulse, our afternoon lull, and then our evening pulse, and then it's lowest at night. That is not in sync with the amount of power generated by solar, right? So notice here, solar is ripping during the middle of the day when we're not using that much power. So the biggest problem is that it's the curvature or the kind of change in solar energy is not in phase with when we want that energy. So that really introduces the kind of the biggest problem and also the holy grail of renewables. We don't have a way to store this, right? So there are no batteries large enough to power, a town of 100,000 people, right? There are some small batteries, much smaller places, but even those are incredibly inefficient. So the challenge is, what do we do with all of this excess power, and how do we offset our power demands in a time where this clean power isn't being generated? So again, that's the holy grail, power storage in the context of not only solar, actually. This is true with wind, less true with water. If we think about the other power types that we've talked about so far, fossil fuels, coal, oil, natural gas, that power plant is chugging along, producing the same amount of power all day, every day. And actually, if you have some warning, you can even kind of throttle it up for the evening and throttle it down for the night, because you know what's going to happen. Nuclear does the same, right? Chugs along, producing power. Hydroelectric, also generally the same, not considering the tidal power or wave power, but just standard conventional hydroelectric on a river. River's just flowing, producing power. Solar doesn't work that way. And actually, the problem is compounded when we start to back our focus out further than one day, right? Because, May 15th or whatever the date may be, you have your power curve for that day. Depends on if it's cloudy or if it's sunny. But actually, if we back off and look at the year, this was actually in Germany, or this data is from Germany, and you can see one particular solar array that they had installed. This is the amount of energy generated by that solar array per month over the course of 1 year. So not only do you get this daily peak that's out of phase with our usage patterns, we also get this annual peak where in the summer we're generating far more than in the winter. And so that really becomes the challenge, right? How do we kind of pull the levers and switches and kind of adjust all of our other power sources so that we can deal with solar kind of fluctuating over time? Really, the far and away the number one problem with solar. The other thing that's really interesting is there's this notion of the grid death spiral. This is something that we've been seeing in Germany. They're really struggling with it. Potentially we'll struggle with it here. I would guess if it were to happen somewhere first, it would be somewhere like Hawaii, where you see lots of people installing individual kind of home use solar. So the problem with the grid death spiral is the grid, right? It's our lifeline. It's this network of wires and transformers that move, high voltage or high capacity electricity. It gets stepped up and stepped down. It's brought into our house. It powers our everything, right? Well, the grid requires financial investment and upkeep, right? We have to keep the grid going. We have to replace the transformers. We have to keep the wires, checked in from fraying, to keep branches off of them, and all of that stuff that costs money. So if you're an individual home solar user, you put a few solar panels on your house or your barn or something like that, you are using the grid, because during the day, you're putting energy on the grid, right? You're putting it out for everyone else to use. And then at night, when you want to turn some lights on, you're not generating power, so you're drawing off of the grid. So you're actually using the grid more than anyone else, because you're loading energy on and taking energy off, but you're paying nothing, right? So you're not paying for grid upkeep. And what they've started to see in Germany is there was a small percentage added to the power bill every month for people to essentially kind of fund the upkeep of the grid for grid improvements and grid maintenance. That small percentage, as fewer and fewer and fewer people are actually paying a power bill, that percentage has to rise and rise and rise, which means those households who haven't kind of gotten off of the grid, or those households who haven't installed individual solar, are paying a higher percentage for grid upkeep, and so their power rates are getting incrementally kind of cranked up, right? Their power rates get higher and higher and higher, and everyone else is not paying their power bill, essentially. So grid collapse is a pretty significant deal, and actually it's highlighted the fact that there's some pretty big structural changes that will have to happen if we really scale up solar. Well, the next problem with solar, money, 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 money. When photovoltaic was first invented in the 1940s, the cost of building one superconductor kind of solar panel was absurd, right? Just not useful, but it was relatively okay to put together for a scientific experiment, right? To write a paper and do some research on it. That's started to change a little bit. You can see here in this diagram, there's a lot of averages here, but this is essentially the cost per state that you would have to pay to offset your annual power usage, or essentially to bring your bill to zero. You can see here in Idaho, it's about $17,000, so a $17,000 investment to bring your monthly power bill to zero, which means, okay, that's a lot of money, right? So you're paying $17,000 to not pay your $100 power bill. Obviously, you kind of have to get some paper and pencil out and scratch this out. Generally, payoff is in the order of 15 to 20 years. So after about 15 or 20 years, your initial investment for those solar panels has paid off, and you're basically getting free power after that, right? So your 17 grand has been paid off in power bills, and then we're moving forward. So that introduces another kind of interesting concept, is that solar technology and efficiency changes with time, right? Solar panels get better and better and better. The ones that were made 20 years ago are not the same ones that are being made now, slightly more efficient. But generally people say there's a 20 to 25 year useful period out of a solar panel, meaning after about 25 years you'll have to replace it. So if you get 17 years down the road and you finally paid off your solar panels, you basically get 5 years of free energy before you're going to have to replace those solar panels. But that makes a lot of assumptions, right? That makes an assumption that in the future solar panels are going to cost the same, which is not a safe assumption. So things do change and technologies get better and things progress forward. So thinking about price, this is a great diagram here that actually shows, from the mid-70s to today. So that you can see here in red on this graph, this is showing price, so in dollars per watt generated by solar. So it kind of helps us normalize, different solar arrays. And notice that in the mid-1970s, really when people were first starting to get excited about solar, we're in the $100 per watt realm. So really, if you were, totally rich, you could do something like this. Actually, so famously in the late 70s, Jimmy Carter installed solar panels on the roof of the White House to generate electricity, and it worked. It was great. It was a big symbolic measure, kind of our transition to renewable energy sources. The subsequent president took them all down, right, and made a big to-do about these damn solar panels. Anyways, not trying to get into the politics, but again, going back to our dollars per watt, notice that really in the early 90s, things come down pretty significantly. And actually, as we move forward in about 2010, there's another significant drop. We're kind of the 2005 to 2010, there's another significant drop, and we're currently down to, shy of 50 cents per watt. And like I said, you can go to Harbor Freight Tools and you can spend $50 on a solar panel and generate enough power to charge up your RV. So financially, it's much, much, much more reasonable now than it used to be, especially if you're looking at replacing these things in 20 years. And then shown here in blue, this is the installed solar capacity globally. And so you can see again, really in the early 2000s, prior to that it was fairly low. It was kind of a wonky cool thing. You could have some solar power. But as we get into the early 2000s, we see this just skyrocket. And frankly, when we think about what that means, that really is going to be what causes this grid kind of death spiral, right? So we can see that globally, so many more people have installed solar to take care of their needs and are basically getting out of paying their power bill. There's many solar companies that actually do a rental program, so you can rent or lease solar panels for 10 years, and then they'll come and replace them. And so if you're leasing them, you're paying $40 a month to lease your panels. That's $40 a month every month, no matter what, right? So your power bills don't fluctuate with the seasons like they do for the rest of us. And that solar leasing company is essentially getting the money that would have gone to the power company. Not that the power company needs more money, right? So the last problem we're going to talk about really has to do with materials. So generally, these things are made out of silicone, right, as a superconductor. Well, silicone, maybe you remember this from our geology section in this class. It is incredibly common, right? Sand, silicon dioxide, quartz. So silicone, no problem. We can find that everywhere. But kind of getting into the technology, that's not the end of the story. There needs to be a lot of metals consumed, and in particular, we start to enter the realm of what we call rare earth elements or rare earth metals. And we'll examine these a little bit more in the case of metals, which we're getting close to talking about. But solar panels in particular use one of the rare earths called indium. And indium is kind of a wonky thing. It's this esoteric kind of rare earth metal. And you can see here, this is a great infographic that lets us know some things about indium. So as you can see, usage, I know this all looks kind of wonky from like a financial point of view, but usage is increasing at about 7% per year. And one of the things is there's just very few industries who are using it, but they need it, right? And you can see that's kind of one of the concepts, is this is driven by a very small group of users, particularly in the development of LCDs, so flat screen televisions, but also in photovoltaics. Now, when we look at indium, and the problem with rare earths is that, well, they're not incredibly rare, as the name would lead you to believe, but we as a nation famously do not have a lot of those resources as a geological resource. Remember this roll of the dice. So this is 2018 in tons of indium produced per country. We're in the gray square, or we're in the gray pie piece, right? We're in with the other. We don't have significant reserves of rare earths of any kind to really be a leader in this realm, and that's problematic because this is really the future, right? Rare earths are what make iPhones possible, flat screen TVs, computer monitors, they make your hard drives faster. All of that stuff is enhanced by this group of metals known as the rare earths. We don't have very many. So here you can see actually this is kind of global rare earth distribution. So we have some, particularly they were at a mine called the Mountain Pass Mine, which is in California. It was shut down in the 90s due to kind of egregious environmental offenses. They were doing some pretty bad stuff there. They got it shut down. But now we're pushing 20 years later, and there's talk of firing Mountain Pass back up, getting a Superfund project, and they're cleaning it up and getting it able to mine again. But again, when we look at the balance of rare earths, China's running the show, right? So China, in a large part, holds the kind of keys to the future, right? They hold the rare earths that we don't have access to, but we need for our technology. And so really, solar is the first place we're going to hear about this, but we're going to hear about it over and over and over again because that becomes really apparent when we start to look at technology and its reliance on this very specific group of elements that we call the rare earth metals. Again, not particularly rare, but they're not as abundant as, like iron or copper or something like that. Okay, so that's going to finish us up with solar. We got through low quality solar, heliostats, photovoltaic, and some of the problems. And the next thing that we're going to get into is wind and geothermal, and then we'll be done with renewables. All right, I'll talk to you later. Bye.